what we haven't really considered yet is the extent to which stereochemistry can be involved with elimination reactions. In the following problem, we're going to do an E2 mechanism with this molecule, and we're going to see how a lot of the concepts we've talked about so far can be integrated with even just one reaction. So we're doing an E2 mechanism, and as always, you want to figure out who the players are. So one thing to consider is, where are our beta protons? Well, on the left, we know we have one beta proton here, and on the right, we know that we actually have a beta proton, on a chiral center, and it's actually going to be on a dash if we draw it out. So we have two choices we can work with, and for this problem we're actually going to start with the beta proton on the right. Before we go farther, we'll want to say, okay, what's our leaving group? That would be the iodine. Good leaving group, it'll be fine, we'll be forming the double bond here. So as we start, we're pretty familiar that we're going to have our ethoxide come in and abstract the proton, and we'll be working the one at the right. But here's the problem. One thing that we haven't seen so far is that with E2 mechanisms we require anti-paraplanar arrangement in order to do the elimination. So how do we achieve that? The idea is we want to put the leaving group and the proton that we're abstracting on opposite sides of the bond. We want to put the bond, the double bond we're forming in between them. Well, how can we make sure that we're achieving that by rotating around the single bond? We can use Newman projection. So let's say I'm looking down, if I draw an eye, and we're looking down this way. So if I draw my Newman projection down here, I would have the iodine coming to the right, that proton that's sharing that position, and we'd have the isopropyl group. Now for everything else, we'd have the hydrogen over here, a methyl group, and then the other isopropyl group. So the idea here is we want to turn either front or the back. I usually turn the front. We're going to turn the front until we get this iodine on opposite sides of the hydrogen that's on the beta hydrogen. So if I turn the iodine or the front groups this way, then what I get is I'll draw the back groups again where they were, and then we will draw the front groups. So iodine's right here, the isopropyl group would be right here, and our other hydrogen that we're not really paying attention to would be right here. So now we can see how the iodine and this hydrogen are actually on opposite sides of the double bond that we're creating, which we're looking straight down. So when we consider that, if I kind of redraw what I had without the iodine and the hydrogen, once we've done the abstraction, I see that, let's see, the isopropyl group is actually going to be on the same side of the double bond as the other isopropyl group. And then the hydrogen that was left here is going to be on the same side as the methyl group, because we can see that we've kind of flattened out. So how does that translate? Well, going back to our mechanism, we're abstracting the proton, electrons are coming down, kicking off the leaving group. So when we do that and we consider what we drew here, we're going to have, the easiest way to draw it is to draw out the double bond. And then you consider, okay, well, both these isopropyl groups are going to be on the same side of the double bond, like this. And then, let's see, we know that we had the methyl group coming off here, and the hydrogen coming off here. So as you can see, if we go back to the original Newman projection that we saw, the two isopropyl groups are both on one side of the double bond, as we said, and the hydrogen and methyl group are on the same side, and we can see that over here. And this would be stereospecific because we need that anti-paraplanar arrangement to do the elimination. Now there's one more part to this problem because this is only looking at one beta proton, which seems like a lot of work. So I'll draw the other parts we'll get is if we abstract this proton over here. Well, if we were to do that, this would be our product. We don't have to worry about the stereochemistry because it's not, this beta proton is not located at a chiral center. Now, of course, that still means that we need the anti-paraplanar arrangement to do the elimination, but it's not going to affect the stereochemistry. So that means we didn't affect the methyl group here, and we still have this. So this actually brings an interesting question. Which of these products might be preferred? And we don't really see a problem like this in the book too often, so let's apply the concepts. Well, we know we prefer a more substituted product. So the first one we did with the stereospecific product, we have 1, 2, 3 carbons attached to the double bond, and over up here we have 1, 2, 3. Well, we have to say they're both substituted to the same degree, so what's something else we can consider? Well, think about this. On the molecule below, the stereospecific product we have these large groups on the same side of the double bond. They're cis to each other. As opposed to here, we have smaller, or I should circle these, relatively smaller groups that are connected to the same side. So we might expect this product up here to be our major product and this to be our minor. Now this is more of a gray area, but this shows how you can always be applying the concepts of organic chemistry, in this case the elimination, to figure out a major product and minor product, even in stereochemistry.